If we were to tell you that the age of the world's oldest nuclear reactor is a staggering 2 billion years, suggesting its existence even before dinosaurs, it raises questions about how such a structure came into being. Perhaps we are witnessing the work of an advanced civilization. Stay tuned for updates and join us in the quest to unravel the history of nuclear energy. In 1942, under the leadership of the renowned Italian physicist Enrico Fermi, the first operational experimental nuclear reactor was built. The dawn of the nuclear energy era saw the successful initiation of the first critical chain reaction in December 1942. The birth of commercial nuclear energy dates back to December 20, 1951, when the B-1 experimental reactor in Idaho generated electricity through nuclear energy. However, what does this frequently mentioned nuclear energy represent in terms of its advantages and dangers? Essentially, to utilize nuclear energy, it must first be released. In this regard, specialists consider two options: nuclear fission, where atoms split into smaller ones, and nuclear fusion, where two atoms merge to form a larger atom. Importantly, this process is not a human-invented reaction, but mirrors how stars generate energy in space. While this energy can be extracted at nuclear power plants for electricity generation, it comes with risks, such as radioactive emissions posing a significant threat to humans and the environment. Recognizing these risks, the German government decided to completely abandon the high-risk technology of nuclear energy a few years ago, especially in light of the dramatic events at Fukushima in 2011 and Chernobyl in 1986. This decision seems highly understandable in retrospect. However, aside from unforeseen accidents, nuclear energy is associated with serious complications. Primarily, the disposal of radioactive waste is not only extremely complex and dangerous, but also requires several centuries before nuclear waste stops emitting radioactive radiation. Additionally, since nuclear reactors have a limited lifespan, there's a constant need to build new power stations, requiring substantial financial investments. Nevertheless, considering all these challenges, it's essential not to forget that nuclear energy has significant advantages. For instance, it sharply reduces the consumption of fossil fuels like coal and oil, resulting in fewer harmful emissions. Therefore, nuclear energy also contributes to mitigating global climate change. In terms of efficiency, no other process comes close to nuclear energy. In fact, nuclear reactors require only a small amount of fuel to generate a substantial amount of energy, reducing not only raw material consumption but also the costs associated with extraction, transportation, and processing. In June 1972, nuclear scientists made a peculiar discovery at the uranium enrichment plant in Pierre-Latte, located in southeastern France. Indeed, specialists noticed an intriguing shortage of uranium-235 during the processing, considering that each gram of fissile material in such a plant should be meticulously accounted for. This unexpected discovery posed a real problem. The complexity lay in the isotopic ratio of uranium in the samples. The main rule is that natural uranium contains 3 isotopes in equal proportions: over 99% uranium-238, 0.7% uranium-235, and 0.005% uranium-234. The issue was that instead of the usual 0.7%, the share of uranium-235 was only 0.06% in the 1970s. How was this possible, and what was the mystery behind this loss? Further research allowed scientists to trace the origin of this mysterious circumstance. The uranium ore used was coming from the Central African state of Gabon, and contained significantly less uranium-235 than ore from other parts of the world. This finding, causing a mix of concern and confusion among scientists, led French nuclear experts to immediately search for this unusual uranium ore. Subsequent analysis revealed one of the most remarkable discoveries in recent history: a historic nuclear reactor. This type of combined uranium is found only in nuclear reactors burning uranium-235. Researchers sought the reactor where this material could have been produced. On September 25, 1972, a headline emerged that seemed incredible then and now. Experts declared that the combined uranium originated from a nuclear reactor in Gabon, which had been dormant for 2 billion years, precisely in the uranium mines of Oklo near the town of Franceville. According to official reports, the nuclear reactor was not a legacy of a vanished advanced civilization, but rather a natural occurrence. Naturally, the deposit of uranium with a sufficiently high content of uranium-235 to sustain a self-sustaining reaction had been in operation for over 50 years. Since this astonishing announcement, leading experts still regard the discovery at Oklo as one of the most unusual natural phenomena of all time. Since then, the Oklo reactor has served as the basis for some innovative research, particularly in studying the ecological consequences of burying nuclear waste. Since the primitive reactor began operating 2 billion years ago, it provides clues about how fundamental constants in the universe may have changed over such a vast timescale. Delving into the mysteries, the first puzzle that scientists managed to unravel in 1972 was how a natural nuclear reactor could function. Until that moment, nuclear scientists had presumed that such processes couldn't occur in nature. In the backstory, natural uranium typically contains only 0.72% uranium-235. But for practical use, it needs to be enriched to about 3 to 5% uranium-235. So how did Oklo have such a high concentration of uranium-235? The answer lies in the fact that uranium-235 has a shorter half-life compared to other uranium isotopes. Therefore, in the distant past, it must have been present in much larger quantities. For instance, when the solar system formed, around 17% of uranium was uranium-235. Over time, this percentage steadily decreased. About 2 billion years ago, the uranium ore in Gabon contained around 4% uranium-235, a concentration sufficient to initiate a self-sustaining nuclear reaction. In this process, the uranium-235 atoms split into 2 smaller nuclei and several neutrons, which in turn split more atoms in a continuing chain reaction. However, to contain the highly energetic particles that usually escape rapidly, nuclear reactors typically include a material that slows down neutrons, preventing them from interacting with other uranium atoms. In the case of the natural reactor in Gabon, water turned out to be a particularly suitable neutron moderator. The crucial cornerstone of the reactor was the presence of water seeping through the uranium ore, which had fascinating consequences for its operation. In detail, specialists propose that the Oklo reactors operated in pulses. When water entered the rock, it slowed down neutrons, facilitating the chain reaction. As the rock's temperature increased, water evaporated, disrupting the interaction between neutrons and primitive nuclei, halting the chain reaction. Over time, as the rock cooled again, water could re-enter, restarting the process. Scientific calculations suggest that the chain reaction likely continued for about 30 minutes before halting for approximately 2 hours. In more detailed terms, the pulsating process probably occurred over 300,000 years. While active, these reactors were powerful entities, and the conditions at that time were likely similar to those prevalent in modern pressurized water reactor systems. These insights offer captivating glimpses into the functioning of these ancient reactors. However, while French nuclear scientists analyzed the Oklo site, they identified not just one, but a total of 17 reactor zones, grouped over an area of several square kilometers. Some of these structures were near the surface and showed signs of weathering, while others were located up to 400 meters deep. Consequently, they remained virtually untouched over time. In addition to uranium-235, numerous fission byproducts, including fragments of zirconium, iridium, neodymium, and cerium, were found in the Oklo reactors. The existence of these fission byproducts is of special interest to specialists. As is well known, one of the significant challenges facing the nuclear industry is finding ways to manage radioactive waste. One straightforward approach is to bury contaminated waste. However, what will happen to these materials millions of years from now is a question that the Oklo reactors could provide valuable insights into. Scientists have made the remarkable conclusion that uranium and most rare earth elements have undergone minimal mobilization in the last 2 billion years. From this, they conclude that if natural waste can be successfully localized in Oklo, long-term storage and carefully designed repositories seems highly promising. Thank you for watching. Don't forget to give us a thumbs up and subscribe to learn more about the most captivating discoveries of all time. Also, consider checking out other videos on our channel. We've provided links in the description. Now we'd like to hear your thoughts. What comes to your mind when you see the Oklo reactor? Did you know that natural nuclear reactors exist?